Hello, we are Team 9. Last week, we presented the elements that make up the tower part of CCTV headquarters. First, we showed modeling of the core, column, and truss that mainly supports the loads rising vertically. After that, we talked about the order in which the elements, considering the outer were composed and the butterfly node of the joint. The CCTV building is subject to additional loads due to its cantilever beam-shaped structure on the upper floor and its tilted shape. The elements located in the tower are more important to withstand this load. Today we are going to focus on two methods that have been used to withstand these additional loads. The first is the climbing system used for uniform intensity expression of the core. We plan to show how this system was introduced and how it works. The second is a monolithic structure that makes the building itself work as a single structure. Let me tell you about the construction method of this structure that increases resistance by dispersing the load. The role of the core is much more important in tilted buildings, especially like the form of CCTV headquarters, because these buildings are primarily designed of the vertical axis. The load on the building is asymmetrically distributed. Consequently, this asymmetric load generated additional moments and torques due to the influence of gravity, which directly affects the structural stability of the building. In a typical vertical building, the core is responsible for about 30% to 70% of the vertical loads and 20% to 50% of the horizontal loads. However, in tilted buildings such as CCTV headquarters buildings, the core will support 40% to 80% of the vertical load and 30% to 60% of the horizontal load. It can be seen that this increased load is because the tilted building concentrates the load more to one side, which required greater torsion and bending resistance in the core. In this way, the tilted shape of the building has further highlighted the importance of the core to resist additional moments and loads during the construction of the CCTV building. The core of the tilted building was not suitable with traditional construction method, and special method we needed to safely and quickly build several vertical cores of the high-rise building. Under these circumstances, climbing concrete systems were considered a stable solution. Climbing systems contributed greatly to the uniform and rapid process of concrete pouring to build the core of CCTV with improved integrity and increased strength. Furthermore, even in Beijing's climate with high wind and high weather fluctuations, climate impacts were minimized and uniform concrete strength expression was effected by skipping decomposition and assembly processes through automated systems. So let's look at the principle of how this climbing concrete system is actually installed in a construction site and moved upstairs. The climbing concrete system consists of three main components: formal climbing brackets and hydraulic or mechanical lifting systems. The difference between hydraulic and mechanical lifting is that the former rises on its own through the automatic system, and mechanical lifting is a method of using a crane. In the mechanical method using cranes, the availability of cranes greatly affects the speed of work. So in the case of CCTV, where many cranes were already used for material transportation, a hydraulic system method was double. In addition, the CCTV construction site chose a hydraulic climbing system due to the nature of the hydraulic jack, which is not significantly affected by weather conditions and the stability of workers in high-rise work. Then, we will show you how the hydraulic automatic system works through the 3D modeling we produced it. The first step is to install the formwork. In a project using a climbing concrete system, the process of installing the formwork on the initial floor is traditionally reinforced and concrete is poured after the formwork is installed. This is an important step to provide structural support for the climbing system and to provide space for the installation of hydraulic units and breakers. The formwork is then secured to the breakers, which are securely attached to the building's main concrete structures, and the work that is also installed in and out of the building. The second set of breakers is now connected, and the hydraulic jack is also connected between the upper and lower brackets. The climbing brackets support the formwork and allow an entire system to move up at the same time. These brackets are controlled by a strong hydraulic system and are used to lift the system to the next floor when work on each floor is completed. The hydraulic lifting system moves the bracket vertically with the formwork. When the hardening of concrete in the floor is complete, the hydraulic jack opens and pushes the structure upward. The moved upper brackets are clamped and secured, the open cylinder is closed, and the lower bracket is moved up too. When the workers reach the new floor, the system pauses and concrete pouring process. After the concrete has hardened, the hydraulic system is reactivated to move the entire formwork and climbing bracket upstairs. This process is repeated and the building gradually rises. Thanks to this principle of climbing concrete system, we were able to build the core of the CCTV headquarters at a high speed based and stability and efficiency. It was a core built with such a powerful automation method, but due to the tilted shape of the CCTV headquarters, we had a problem that not all cores were constantly connected to the end floor like the animation. This had led to a lack of elements called cores that bear most of the load, as I said earlier. To address these issues, CCTV adapted a monolithic structures. Monolithic structures are designed so that each part of the building works like a huge single structure so that each part is connected to each other and evenly distribute the load on each part, increasing structure stability. The theoretical monolithic structure is constructed as follows. First of all, the lever is located in the main location. In the case of CCTV, a reinforced mechanical joint was used in this process to strengthen the joint of the reinforcement than the traditional joint. The typical traditional joint simply holds the reinforcement by the addition of concrete, so when there is a problem with concrete, the joint collapses in an instant. That among the mechanical joints that supplemented this, CCTV used high-quality coupler joints. Coupler joints compensate for the structural shortcomings of buildings tilted 6 degrees because there is no problem with lever joints even if concrete is broken. At the same time, construction work is relatively easy, enabling accurate and solid construction of building in a short time. As above, the columns and wall slabs are placed continuously after the reinforcement is deployed, and the air bubbles are removed through the vibrator to ensure that the concrete penetrates completely into the reinforcement. This hardened concrete structure is much stronger than the divided structure, maximizing resistance to external loads. At the construction site of the CCTV headquarters, columns and cores were erected and walls and slabs were continuously poured to use the monolithic structure. The building was constructed to operate the single integrated structure as each component was closely connected to each other and placed. This made it easier for CCTV buildings to deliver loads with a monolithic structure that has a solid core and a structural sense of unity. Today we learned about the construction process of the structures that make up the tower part of the CCTV headquarters building. Thanks to the use of climbing systems and monolithic structures, CCTV's tower has solid strength and stability. Next week, we are going to talk about a cantilever-shaped structure that placed on top of this tower. We plan to focus on the cantilever-shaped construction method that had to be joined in the air and the principles used in the process. Thanks for listening to our presentation. We were Team 9.